Start with the reality that the most accessible asteroids are not the giant cinematic monsters often shown in fiction, but relatively small near-Earth objects that already pass close to our planet with low relative velocities. These are the ideal candidates for capture and redirection because changing the orbit of a smaller asteroid requires dramatically less energy than attempting to move a massive body. In practical mission planning, the key is not brute force but orbital efficiency. Engineers look for asteroids whose trajectories already resemble Earth's orbit, allowing small adjustments to produce major long-term changes. The first actionable principle is accurate detection and characterization. Capturing an asteroid is impossible without understanding its composition, rotation, density, and internal structure. Many small asteroids are not solid rocks at all. They are loosely bound rubble piles held together by weak gravity. Applying too much force in the wrong way could fragment the target into multiple uncontrolled objects. This means reconnaissance missions are essential before any capture attempt. Spacecraft equipped with radar mapping systems, spectrometers, thermal imagers, and gravimetric instruments can determine whether the asteroid is metallic, carbon-rich, porous, or structurally unstable. Rotation control becomes one of the most overlooked engineering challenges. Many small asteroids spin rapidly, some tumbling unpredictably through space. Before redirection can safely begin, the rotation may need to be slowed or stabilized. One effective approach involves attaching low-thrust ion propulsion systems that gradually alter angular momentum over time. Another method uses reaction masses or tether systems to redistribute forces across the asteroid's surface. The important lesson is that patience is often more effective than raw power in orbital engineering. Small, continuous adjustments applied over months or years can produce dramatic trajectory changes with relatively little energy expenditure. Choosing the right propulsion strategy depends heavily on mission goals. If the objective is scientific study, the asteroid may only need to be redirected into a stable orbit near Earth or the Moon. In this case, solar electric propulsion becomes highly attractive because it offers efficient long-duration thrust with minimal fuel consumption. Ion engines accelerate charged particles at extremely high velocities, producing gentle but continuous force capable of slowly reshaping an asteroid's orbit. These systems are especially practical in deep space where there is no atmospheric drag to overcome. For resource extraction missions, planners must prioritize asteroids rich in water, nickel, iron, platinum group metals, or carbon compounds. Water is especially valuable because it can be separated into hydrogen and oxygen for rocket fuel and life support systems. In many future space economies, water-rich asteroids may become more strategically important than precious metals because transporting fuel from Earth is extremely expensive. Redirecting a small water-bearing asteroid into lunar orbit could effectively create an orbital refueling station, dramatically lowering the cost of deep space exploration. Capture mechanics require extraordinary precision. One practical strategy involves enclosing the asteroid within a containment structure such as an inflatable bag or deployable net system. This method distributes forces evenly and reduces the risk of fragmentation. Another approach uses robotic anchoring systems that drill into the surface and apply controlled thrust through multiple attachment points. Surface interaction is far more complicated in microgravity than it appears. Anchors can fail if the material is too loose, while excessive drilling force may eject debris into surrounding space. Orbital destination planning is equally important. Redirecting an asteroid directly toward low Earth orbit introduces significant risk because any navigation failure could threaten the planet itself. Safer options include distant retrograde lunar orbits, Earth-Moon Lagrange points, or stable high Earth orbits where gravitational conditions are more predictable. These locations allow long-term access for mining or research while minimizing collision hazards. Thermal effects become increasingly important during redirection missions. Asteroids absorb solar radiation unevenly, and this creates tiny but continuous forces known as the Yarkovsky effect. Over time, sunlight itself can subtly alter an asteroid's trajectory. Engineers must model these effects carefully because even small deviations can accumulate over millions of kilometers. Surface coatings or reflective materials may eventually be used to intentionally manipulate solar heating as a passive steering mechanism. Autonomous navigation systems are essential because communication delays make real-time manual control impractical during many phases of the mission. Spacecraft must independently monitor trajectory changes, anchor stability, propulsion output, and rotational dynamics. Machine learning systems may become especially useful for identifying structural weaknesses or predicting how the asteroid responds to applied forces. Future capture missions will likely rely heavily on robotic decision-making, with humans supervising broader mission goals rather than controlling every maneuver directly. Radiation and debris management are also critical operational concerns. Mining or redirecting an asteroid can release clouds of dust and fragments traveling at dangerous velocities. Even tiny particles become hazardous in space because there is no atmosphere to slow them down. Spacecraft involved in capture operations require reinforced shielding, debris tracking systems, and carefully controlled work zones to minimize collision risks. Some mission concepts even propose electrostatic fields to repel fine dust particles from equipment surfaces. Economic viability depends on reducing launch costs and increasing in-space manufacturing capability. Capturing asteroids only becomes sustainable when spacecraft can repair themselves, produce components from off-world materials, and refuel beyond Earth. This is why asteroid redirection is closely tied to the broader development of space infrastructure. The real breakthrough may not come from one dramatic mission, but from gradual improvements in robotics, propulsion efficiency, autonomous systems, and orbital logistics. Legal and ethical questions are becoming increasingly important as well. Ownership rights over redirected asteroids remain legally complex under current international space treaties. Any mission capable of altering asteroid trajectories also carries dual-use implications because technologies designed for redirection could theoretically be weaponized. Transparency, international cooperation, and shared monitoring systems will likely become necessary to prevent geopolitical tensions surrounding asteroid operations. One of the most valuable long-term applications may involve planetary defense. Techniques developed for capturing and redirecting small asteroids directly improve humanity's ability to prevent dangerous impacts in the future. Every mission teaches engineers how different asteroid types behave under controlled force application. This knowledge becomes crucial if humanity ever needs to alter the course of a genuinely hazardous object. In that sense, asteroid capture technology serves both economic and protective purposes. The deeper significance of asteroid redirection lies in what it represents technologically. Humanity has historically adapted to environments on the surface of a single planet. Redirecting asteroids marks the beginning of large-scale celestial engineering, where entire natural objects become part of human infrastructure. Instead of launching every resource from Earth, civilizations could eventually harvest metals, water, and construction materials directly from space itself. This fundamentally changes the economics of exploration because future habitats, spacecraft, and industrial systems may be built from extraterrestrial material rather than lifted out of Earth's gravity well. The most successful missions will likely embrace flexibility rather than relying on one rigid design philosophy. Different asteroids demand different strategies depending on composition, rotation, orbit, and mission objectives. Some may be nudged gently over years using ion propulsion. Others may require robotic stabilization systems, gravity tractors, or solar sail-assisted maneuvering. The field rewards adaptability, careful observation, and long-term planning far more than dramatic interventions. Every small asteroid drifting through the solar system carries more than rock and metal. It carries untouched material from the earliest era of planetary formation, preserved for billions of years in the cold vacuum of space. Capturing and redirecting these objects is not only about mining resources or advancing technology. It is about learning how to interact with the architecture of the solar system itself in a deliberate and controlled way, transforming ancient celestial remnants into stepping stones for humanity's expansion beyond Earth.